Welcome to our deep dive into Transformers, one of the most revolutionary architectures in the field of artificial intelligence. In this video, we'll explore what makes Transformers unique, how they work, and why they've become the backbone of modern natural language processing. Whether you're new to machine learning or looking to deepen your understanding, this journey will clarify the core concepts and practical applications of Transformers. Let's begin by setting the stage with a brief overview of their origins and the problems they were designed to solve. Transformers were introduced in 2017 by Vaswani et al. In their groundbreaking paper, Attention is All You Need. For Transformers, models like RNNs and LSTMs dominated sequence modeling tasks, but they struggled with long-range dependencies and parallelization. The Transformer architecture addressed these limitations by leveraging self-attention mechanisms, enabling models to process entire sequences simultaneously. This innovation paved the way for significant advancements in machine translation, text summarization, and more. Transformers have fundamentally changed the landscape of deep learning. Their ability to handle long sequences efficiently and capture complex relationships in data has made them the architecture of choice for many state-of-the-art models. From language models like BERT and GPT to applications in vision and audio, Transformers have demonstrated remarkable versatility. In this scene, we'll discuss the impact of Transformers on AI research and real-world application. The heart of the Transformer architecture are several key components: the encoder, the decoder, and the attention mechanism. Each plays a distinct role in processing and generating sequences. The encoder reads and encodes the input data, while the decoder generates the output, often in another language or format. The attention mechanism, which we'll explore in detail, allows the model to focus on relevant parts of the input when making predictions. Encoder is responsible for transforming the input sequence into a set of continuous representations. It consists of multiple identical layers, each containing two main sublayers, a self-attention mechanism and a feed-forward neural network. The encoder's self-attention enables the model to weigh the importance of each word in the context of the entire input, capturing relationships regardless of their distance in the sequence. Decoder mirrors the encoder structure, but with a few key differences. It also consists of several identical layers, each containing three sublayers: self-attention, encoder-decoder attention, and a feed-forward network. The decoder self-attention is masked to prevent positions from attending to subsequent positions, ensuring outputs are generated sequentially. The encoder-decoder attention allows the decoder to focus on relevant encoder outputs when producing each token. Self-attention is the core innovation of the Transformer. It allows the model to consider the relationships between all words in a sequence simultaneously. By computing attention scores, the model determines which words are most relevant to each other regardless of their position. This mechanism enables the model to capture context more effectively than previous architectures, leading to better performance on a wide range of tasks. Multi-head attention extends the self-attention mechanism by running multiple attention operations in parallel. Each head learns to focus on different aspects of the input, allowing the model to capture a richer set of relationships. The outputs of all heads are concatenated and linearly transformed, providing the model with diverse perspectives on the data. This approach enhances the model's ability to understand complex patterns in sequences. Within each encoder and decoder layer, a position-wise feed-forward neural network processes the outputs of the attention mechanisms. This network consists of two linear transformations with a ReLU activation in between. It operates independently on each position, enabling the model to introduce nonlinearity and further refine the representations. Feed-forward networks play a crucial role in enhancing the model's expressive power. Like RNNs, Transformers lack an inherent sense of sequence order. To address this, positional encoding is added to the input embeddings, providing information about the position of each token in the sequence. These encodings use sine and cosine functions of different frequencies, allowing the model to distinguish between different positions and capture the order of words effectively. Layer normalization is applied after each sublayer in both the encoder and decoder. This process stabilizes the learning by normalizing the inputs across the features, which helps the model converge faster and improves overall performance. Layer normalization is a subtle but important detail that contributes to the robustness of the Transformer architecture. Residual connections are another key feature of the Transformer. By adding the input of each sublayer to its output, residual connections help mitigate the vanishing gradient problem and enable the training of deeper networks. This design choice allows information to flow more easily through the network, leading to better learning and improved performance. Input embeddings are the first step in processing raw data. Each word or token in the input sequence is converted into a dense vector representation, capturing its semantic meaning. These embeddings are combined with positional encodings before being fed into the encoder, ensuring that both the content and order of the sequence are represented. Decoder generates the output sequence one token at a time, using the encoded input and previously generated tokens as context. At each step, the decoder predicts the next token, gradually building the final output. This process continues until a special end-of-sequence token is produced, signaling completion. Attention scores are at the heart of how Transformers determine which parts of the input are most relevant for each output. These scores are calculated using queries, keys, and values derived from the input embeddings. By computing dot products and applying a softmax function, the model assigns weights to each input position, guiding the focus during processing. In the attention mechanism, queries, keys, and values are linear projections of the input embeddings. Each word in the sequence is transformed into these three vectors, which are then used to compute attention scores. This process allows the model to compare each word with every other word, identifying important relationships and dependencies. Softmax function is used to normalize the raw attention scores into probabilities. After computing the dot products between queries and keys, the softmax ensures that the resulting weights sum to 1. This normalization step is crucial for guiding the model's focus and ensuring that attention is distributed appropriately across the input sequence. Masking is an essential technique used in the decoder's self-attention mechanism. By masking future positions, the model prevents itself from peeking ahead when generating outputs. This ensures that each prediction is based only on known information, maintaining the integrity of the sequence generation process. Transformers achieve their power by stacking multiple encoder and decoder layers. Each layer refines the representations learned by the previous one, allowing the model to capture increasingly complex patterns. This deep stacking is a key reason for the impressive performance of transformer-based models on challenging tasks. Parameter sharing is sometimes used in transformer models to reduce the number of trainable parameters. By reusing weights across layers, models can become more efficient and require less memory. This technique is particularly useful in resource-constrained environments or when deploying models at scale. Training a transformer involves optimizing millions, sometimes billions of parameters using large datasets. Techniques like atom optimization, learning rate scheduling, and regularization are commonly employed to ensure stable and effective training. The process can be computationally intensive, but the results are often state-of-the-art models capable of impressive feats. Most modern transformer models are first pre-trained on massive corpora using unsupervised objectives, such as masked language modeling. After pre-training, they are fine-tuned on specific tasks with labeled data. This two-step process allows models to learn general language patterns before specializing, resulting in better performance and adaptability. Transfer learning is a powerful benefit of transformer models. By leveraging knowledge gained during pre-training, these models can be quickly adapted to new tasks with relatively little labeled data. This approach has enabled rapid progress in fields like natural language understanding, question answering, and sentiment analysis. Transformers have become the foundation for many state-of-the-art natural language processing applications. From machine translation and text summarization to sentiment analysis and question answering, their ability to model complex language patterns has set new benchmarks across the board. In this scene, we'll highlight some of the most impactful NLP applications powered by transformers. Beyond language, transformers are making waves in computer vision. Vision transformers, ViTS, apply the same attention-based principles to image data, achieving impressive results on tasks like image classification and object detection. This cross-domain success demonstrates the versatility and power of the transformer architecture. Transformers are also being used in audio processing and multimodal tasks that combine text, images, and sound. Their ability to model complex dependencies makes them ideal for speech recognition, music generation, and even tasks that require understanding multiple data types simultaneously. This flexibility is driving innovation across diverse fields. One of the standout features of transformers is their scalability. As models grow larger and are trained on more data, their performance continues to improve. This scalability has led to the creation of massive models like GPT-3, which can generate human-like text and perform a wide range of tasks with minimal supervision. Despite their strengths, transformers come with significant computational costs. Training and deploying large models require substantial hardware resources and energy. Researchers are actively exploring ways to make transformers more efficient, such as model pruning, quantization, and distillation, to reduce their environmental and financial impact. Memory usage is another challenge for transformer models, especially as they scale. The self-attention mechanism requires storing large matrices, which can quickly exhaust available memory. Techniques like sparse attention and memory-efficient architectures are being developed to address these limitations and enable the training of even larger models. Understanding how transformers make decisions remains a challenge. While attention maps provide some insight into which parts of the input the model focuses on, interpreting the inner workings of large models is still an active area of research. Improved interpretability will help build trust and transparency in AI systems. ERT, or bidirectional encoder representations from transformers, is a popular variant that uses only the encoder part of the architecture. BERT is pre-trained using masked language modeling and next sentence prediction, making it highly effective for understanding context and relationships in text. It has set new standards in tasks like question answering and text classification. GPT, or generative pre-trained transformer, is another influential variant that uses only the decoder part of the architecture. GPT models are trained to predict the next word in a sequence, enabling them to generate coherent and contextually relevant text. Their generative capabilities have made them popular for tasks like text completion and creative writing. T5, or text-to-text transfer transformer, frames every NLP task as a text-to-text problem. By converting inputs and outputs into text, T5 achieves remarkable flexibility and performance across a wide range of tasks. This unified approach simplifies the architecture and training process, making it easier to apply to new challenges. Vision Transformers, VTS, adapt the transformer architecture for image data. By splitting images into patches and treating them as tokens, VTS apply self-attention to visual information. This approach has led to state-of-the-art results in image classification and demonstrates the adaptability of transformers beyond text. Longformer is a transformer variant designed to handle long documents efficiently. It uses a combination of local and global attention patterns to reduce memory and computation requirements, making it suitable for tasks like document classification and summarization, where input sequences can be very lengthy. Transformer Excel introduces recurrence into the transformer architecture, allowing it to model longer-term dependencies by reusing hidden states from previous segments. This innovation enables the model to process much longer sequences without running into memory constraints, making it ideal for language modeling and time series analysis. Reformer is a transformer variant focused on improving efficiency. It uses techniques like locality-sensitive hashing and reversible layers to reduce memory and computation requirements. These innovations make it possible to train very large models on limited hardware, expanding the accessibility of transformer technology. Which transformer introduces a mixture of experts approach, where different parts of the model are activated for different inputs. This design allows for massive scaling while keeping computation efficient, enabling the training of models with trillions of parameters. Switch transformers represent the cutting edge of scalable AI architectures. Transformers are widely used in industry, powering applications like search engines, chatbots, recommendation systems, and more. Their ability to process and understand large volumes of data makes them invaluable for businesses seeking to deliver smarter, more personalized experiences to users. The open source community has played a crucial role in the rapid adoption of transformers. Libraries like Hugging Face Transformers provide easy access to pre-trained models and tools, enabling researchers and developers to experiment and innovate quickly. This collaborative ecosystem continues to drive progress in AI. Future of transformers is bright, with ongoing research focused on making models more efficient, interpretable, and capable. Innovations like sparse attention, modular architectures, and better training techniques promise to push the boundaries of what transformers can achieve. As these models continue to evolve, their impact on AI and society will only grow. As with any powerful technology, transformers raise important ethical questions. Issues like bias, fairness, and responsible deployment must be addressed to ensure that these models benefit society as a whole. Researchers and practitioners are working to develop guidelines and tools for ethical AI development and use. Let's recap the key points covered in this deep dive. We explored the architecture of transformers, including encoders, decoders, and attention mechanisms. We discussed their applications, challenges, and various model variants. Understanding these fundamentals provides a solid foundation for further exploration and practical use of transformer models. If you're interested in learning more about transformers, there are plenty of resources available. Research papers, online courses, and open-source libraries provide in-depth knowledge and practical tools. Engaging with the community and experimenting with models are great ways to deepen your understanding and stay up to date with the latest developments. Thank you for joining this comprehensive exploration of transformers. Their architecture and functionality have transformed the field of artificial intelligence, enabling breakthroughs in language, vision, and beyond. As research continues, we can expect even more exciting developments. Stay curious and keep exploring the world of AI.